So I want to continue our discussion on conservation of energy. We'll do a few more practice problems where we go over just how we would use the method that I showed before. All right, so here's the next question. Pause video, work stuff, and we'll go in a second. All right, so if we read the question, what ends up happening is this object starts with zero kinetic energy and then somehow gains kinetic energy. And because they tell us that there was a force applied to the ball, I know that I had to have started with work. If I drew a picture of what happened, we have a ball that's stationary, a force is applied to it, and then it begins to move. So, what I'm going to do is I'm going to use the equation work equals kinetic energy. Since they don't give me the kinetic or the work energy right off the bat, and they don't say anything about it, I'm going to plug in the equations FD for work and 1 half mv squared for kinetic energy, plug the numbers in that I had before, and I end up getting that the distance is 0.0025 meters. All right, here's the next question. Pause the video, work self, and we'll go over in a second. All right, once again, if I try to visualize what's going on, we have this stunt woman at some height. They fall off the cliff, and we want to find the speed just as they're about to hit the ground. So we have an object. We have a situation where the object starts with gravitational potential energy, and it's going to end with kinetic energy since it's moving. You want to make sure that you're keeping an eye out for keywords and the types of energies that go with that. So in this case, I'm going to set UG equal to K. Going to plug in the MGH equals to 1 half mv squared. Plug all my numbers in right from the get-go, and end up getting that this final speed is going to be 28.3 meters per second. Again, the key is to identify all the energies that are going on before and after at the 2 points. And you want to keep track of what type of information they're referring to in order to give us an idea of what energies we should be considering. All right, here's the next question. Pause the video, work itself. We'll go over in a second. All right, now if you notice in the question, it mentioned something about the ball being gently pushed off the edge of the tabletop. So you might think that the situation either starts with work and potential, or maybe even potential and kinetic, and then it turns into kinetic energy. It's important to note that a lot of times when they say it's gently pushed, that's their way of saying that that action is negligible. That the amount of force that's being applied is very small, the amount of kinetic energy the object ends up gaining is very small. What we care about is essentially what the major effects are, the gravitational potential and the kinetic energy. A lot of times, as I've said in class, you want to try and keep your blinders on and only focus on the information they're providing that's usable. If I considered that there was work involved, I'd be left at a dead end because there's no way for me to find work. If I thought that there was initial kinetic energy, there's no way for me to actually work with that because, again, there's no information about it. So what I'm going to do is the object starts at the table at the tabletop at some height. So it's going to start with potential. It's going to go to the ground and gain kinetic energy. I can then plug in my equations once again into potential and kinetic. Plug my numbers in. I end up getting that the speed is 10 meters per second. So you should start seeing the pattern here. One thing that I want to point out is you may notice that in a lot of these questions that we're doing, it's one energy equals one energy. That's not going to be the case all the time, especially since the AP1 really likes to hammer in both tricky questions and questions that resemble a lab experiment setup, a real world setup. There's going to be very often, very times where you're going to end up having multiple energies equal to each other. So you could have potential plus work equal to kinetic plus heat, or potential plus kinetic equals kinetic plus heat, or something like that. So you want to kind of keep an eye out for that. Don't just automatically assume that it's one to one energy equal to one energy, because that's the easiest way for you to get into a situation where you underestimate the question. All right, here's the next question. Pause video, works up, and we'll go in a second. All right, so this one's a little bit trickier. I'm gonna have to draw a picture. I don't think I drew a picture for this at all. So we have an object that is going up a ramp, and they want to figure out where it ends up going. Now, this is actually one of the reasons why conservation of energy is so nice. You may have noticed in the previous questions, while I didn't show it, there were ways around using energy. You could have found the force. You could have used the force in the previous question to find the acceleration. Find the acceleration and the speeds to figure out what the distance is. Things like that. You could have used Newton's laws and kinematics, and it would have been just as easy. Here, you'll notice that if we try to use this a slightly different way, it is going to be a lot trickier in order to answer in terms of forces and kinetic energy. In fact, forces and kinematics. It's the energy topic that makes this problem really simple. So we have this box being shot up. At the bottom, it has some initial kinetic energy, and at the top, it's going to end up getting potential energy. And I know that it's going to end up having going to some height h. So what I can do is I can do this to figure out what the height is that the object reaches. Now, notice that this is not what they're looking for. They're actually looking for the distance that it slides up the ramp. So I'm actually looking for this distance here. Oh, yeah, I'm looking for this distance. So what I have to do is use trigs to figure out, now that I have my height and I have the angle, how do I find this? Well, that uses SOHCAHTOA. So sine of the angle equals opposite over hypotenuse, h over d. Solving for the hypotenuse, which is the distance that they're referring to. So it's going to be the height divided by the 37 degrees. And I end up getting 8.31 meters. So that's the actual distance that the box is going to go up. So I mentioned before that conservation of energy has this knack of combining all the units that we've done before. And this is definitely the start of one of those examples. I think the very next question really showcases that a lot more. So you want to make sure that you're referring back to the previous units. But as I said, you'll notice is that it's actually going to be a lot easier dealing with energy, even if it may not seem like it in the future questions. It is definitely easier than using the force and kinematics method, because in those cases you have to play around with components, and you have to make sure that the forces and the accelerations are all going in the right direction. With energy, they're scalars. You don't have to worry about direction. All right, so here's the next question. Pause video, work on itself, and we'll go in a second. All right, now here's one of the nice things about energy. We have a situation where the skydiver is falling out of a helicopter that's at some initial height of 300 meters. Then it falls to 200 meters. And we want to know what is the speed that it reaches. Now, the nice thing is, if you recall, the equation for potential energy isn't just mgh, even though that's what I've been simplifying it as. It's change in potential equals mg delta h. So what I can do, potential energy is very flexible. Even though this object is still at some height and has a potential, I don't really care about that. I'm going to set this point as my 0 point, where the object has zero potential, because that's what I care about as far as the scope of this problem. I just care about it going from here to this point. Even though it's going to fall later on and it's going to fall another 200 meters, that's outside the scope of my problem. I'm only focused on this. So when I do my equation and I do the change in potential equals kinetic, what I'm going to do is I'm going to take the difference in these heights, because this is now 0, and since this is 100 meters above it, the height that I'm going to use is actually 100 meters. When I plug that in, I end up getting 31.6 meters per second. Now, if you didn't like this and instead wanted to compare it to the ground, that's fine. You would have had UG at this point, UG plus kinetic at this point. You would have had the situation where you do MGH, initial, I'll say it, equals mg final height plus kinetic. The masses all drop out because this is going to be 1/2 v squared. And when I move this over to the other side, I'll end up getting h naught minus h, which is exactly what I have here and here and here. Yeah, where I have 300 minus 200. Again, it ends up being the same thing. This is why we're allowed to do this for potential. Because of the direct relationship between height and potential, we can just consider a different point as being zero potential and just worry about those two sections. All right, here's the next question. Pause the video, work itself, and we'll go in a second. All right, now this is the question that I was referring to before, where this one's got a lot going on. And this one actually requires us to go back and kind of think about this in terms of forces, just a little bit. If I look at the problem, so we have a skier starting at the top of the ramp. He starts at 0. I should probably say that. He starts at 0. He travels a distance of 400 meters to this point where he now has some final speed. We want to know what that speed is, and they tell us that there's friction on the snow. So this is where, like I said, a lot of stuff's going on. So if I want to start with energy, I need to start off with what is the energies going on. At the very top, I only have potential energy. At the very bottom, I'm going to have kinetic plus a little bit of energy lost to heat, loss of friction. So my equation is going to start off as UG equals K plus Q. Now, in one of the previous videos, I made a comment that Q is sometimes called the work done by friction. So what I can do is I can replace Q with force of friction times the distance. And that's how I start this problem off. I set the potential energy at the very top equal to the kinetic energy at the bottom plus a little bit of that energy that's being lost to friction. Now, this is the only reason why this question is tricky. Like I said, if it wasn't for the friction, doing this in the energy sense would have been a lot more work, a lot less work than doing it in the forces sense. However, because I need to figure out the forces, I am going to have to look at FBDs and look at that. So let's draw another FBD so that we can see some stuff. Remember when we draw our FBDs, we have the normal force, we have the frictional force, we have this mg sine theta, and this is mg cosine theta. So I'm going to replace force of friction with mu Fn. And mu and Fn is being equal to this perpendicular component of the gravity. So this is going to be equal to mu mg cosine theta. Now, another thing to note is that h and d are representing two different things. D is representing the distance along the ramp. H is referring to the vertical height of the ramp. So I'm going to have to do something very similar to that I did last time, where I used trig to find a relationship because I know the hypotenuse of the ramp, the distance along the ramp. I know the angle, but I don't know the height. So this time I'm going to use sine SOHCAHTOA again. I'm going to use sine to get sine 20 equals opposite over hypotenuse. Solving for h just gets me d sine 20. The reason I'm showing this is because I immediately jumped straight into plugging them in. So I just want to explain why I changed the h to d sine theta and why I changed ff into mu mg cosine theta. Because this ends up getting it so I can actually figure out what the height is, and this allows me to figure out what the normal force is to find the friction. Once I get to this point, now I can kind of clean it up If you wanted to plug, I should actually point out that you may notice that they don't tell us the skier's mass. And this is actually the reason why I had to go through this slightly longer method. If you wanted to, you could have found all these energies individually before you plugged it all in. But because they didn't tell us the height, I had to set up the equation first so that I can ultimately drop all the m's. So I move some things around. I'm going to move this mu g cosine theta d over to the other side. I have a gd on both sides, so I can then have this v squared equals 2gd sine theta minus mu cosine theta. Oh, a little hard to see. I don't know why I rewrote it twice. I plug the numbers in, and I get that the speed is 35.1 meters per second. And that's pretty much it. I think that's probably one of the harder types of questions. I mean, there are some, like I said, some trickier ones that really play on a lot of misconceptions. So you do want to be careful with that. But as far as calculation wise, this is really the extent to the difficulty of the energy stuff. You wouldn't normally see anything more complex than this. All right. Uh, in the next video, I'm going to talk about graphs, so I'm going to leave it off from there. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.